All right, welcome back, everyone. So today we want to start a new topic. Let me full screen this. All right, great. Cool. A light, and here we go. All right. So today I want to talk about cache coherency and multi-core. A couple of things before talking about cache coherency. Number one is uh, let me see if for some reason I don't. Okay. 1, 2, 3, 1, 2, 3. Okay. First thing, quiz 2 is this Thursday. Don't forget about it. It's about branch prediction, out-of-order execution, and cache design. Uh, Everything after basically quiz 1, right? And same format, very similar style, probably same number of questions, very similar type of questions. So you should expect to see very similar things as you saw in quiz 1. If you're CAE students, similar format for you guys as well. I'll post the Zoom link sometime today or tomorrow, probably. Uh, Everybody else, you have to be here in person, and then same story about the sign-in sheet and all. And then the set of rules will be the exact same rules that we had in quiz 1, which is open book and open source. You are not allowed to use internet. You're not allowed to use ChatGPT and equivalent. And then in terms of resources, of course, the 2 homeworks are the best resources for you. And past years' examples of the quiz and the homeworks are always a good resource as well. And again, as I said many times before, if you see discrepancies in the ways that we treat things this year versus previous years, what you should use and the way that we're going to grade your quiz is based on what we said this year. So you cannot refer to the previous years and say, okay, that's what I did. We're not going to give you grades for that, okay? Just keep in mind that, and this is just for the consistency reasons. Ideally, we don't want to have these issues, but these are also inevitable over the years. We keep changing things for various different reasons, and that's why there's a little bit of inconsistency among different versions, but at least we try to be consistent in each given version. And also another thing that I do recommend to do is making sure that you put all the things that you think is relevant in your paper so that we can give you partial grades. Oftentimes we see that people does things but don't really put it into their papers, and it makes it hard for us to give them grades. And they come back at us and say, okay, oh, by what I thought, my thought process was this, and that's how I came up with the answers. But we can only grade you based on what you've written. I cannot grade you based on what you thought. Any questions about quiz 2? Great. CA2. So great job. I think this was the first time we tried this in my undergrad class. I tried it in my grad class. Based on the polling, seems that people liked it as well. I think today I just checked 50 people voted so far. There's a poll on Campus War. I just asked whether you liked it or not. And it was fairly positive. I think 85%, more than 85% liked it. Also, congratulations to our top 3. These are our winners. Do we have Simon, Cyrus, or Sauce here? No, they're busy at home coding. All right, so I might announce it again on Thursday. So Simon, I believe, was the best. Their code, based on at least what I saw on Gradescope, was some form of take. But they are using a different hashing method and also using a different update method. So they didn't use the usefulness the same way that the take used it. At least that's what I understood from the code, just looking at it for a few minutes. But they maybe want to post a little bit. You're welcome to actually share what you did on campus. Cyrus did perceptron-based, so machine learning-based. It was apparently an ensemble of perceptrons, so multiple perceptron, and based on the history, They choose which one they want to use. And Sahas use similar to perceptron, but it's this called piecewise linear branch predictor. So it's so different than the way that perceptron learns. It's more of a, you divide the space into piecewise linear and try to learn that. So it's like a different learning method, if you will. And then use that in order to predict. So your top three was kind of like that. And I'm sure that you guys try various different things as well. Some variation of TAG and G-share and perceptron has been seeing. But I hope that you understood and you learned a new concept and you tried it. And it was also the game aspect was like make it a little bit more fun. I understand that also like creates some stress for some people, which is sometimes inevitable. But the whole point was kind of like gamify it a little bit, so it's making it a little bit different. Any questions about CH2? Yeah. Yeah, so the question is about MPK. It's not bench, it's a metric, yeah. So it's miss per thousand instructions, both for cache misses and for branch predictions. MPKI is a yeah. Mm-hmm. In real systems, so the question is how much memory do branch predictors take up in a real system? By the way, these, based on the reports, they only use few megabytes, which was interesting to see that they didn't use crazy amount of memory. It really depends on the class of the processor. If it's like a very high-end processor, few megabytes is not that much of unreasonable. And also keep in mind that this is stored in hardware, so there are lots of optimization you can do in hardware to compact things. But yeah, maybe a megabyte if you can get like a decent accuracy out of it, it might be possible. I think the actual competition was in order of hundreds of kilobytes. It wasn't megabyte for sure, if I remember. Because this was like part of like an actual competition. So yeah, I would say maybe for lower end, it's more of in the order of hundreds of kilobytes. Mm-hmm. Okay, so let's get back to the lecture. So where are we now? If you remember, I showed you this figure at the beginning, right? This was kind of like our guideline, our roadmap. And we started with like saying that in 70s, we had our first general purpose processor. And then we kind of, from there, we continue going up and up and up. And then in modern days, we have very, very fast processors, about 50,000 times faster than what we had the very first time. And then if you remember, I told you that a big portion of this was because of the technology and the fact that we can pack more transistors and faster transistors. But that also added to the fact that we can pack a lot of microarchitecture optimization. So this kind of sharp increase from 20% to 52% was all thanks to optimizations that we introduced at the computer architecture level. And now you know most of them, right? So you know branch prediction, you know out-of-order execution, you know caching, you know speculation, pipelining, forwarding, all those things. These are all these kind of 30 years of computer architecture. And it's still going, but it's kind of slowing down because really you can do much. Like you, for example, you were at the role of a computer architect when you were designing your brand. You saw that, and the ideas are, you're running out of the ideas, right? So it's kind of like, it's not like a breakthrough that is happening in branch prediction anymore, unfortunately. You can like play with it and make this slightly better, but these are mostly incremental improvement. So we are now at kind of like this phase in early 2000, 21st century, where we no longer can pack more and more transistors into one single chip. The reason for this is that the dynamic power consumption goes so high. In other words, the power density stops being constant and it's actually going up, that if you add more transistors, you need to cool it down, and you cannot cool it down, so you cannot increase the size. The second thing is that when you're building larger chips, the area that you build your chips around is important. And if the chips gets too large, then unfortunately what we call yield, which means how much defect-free, error-free chips we can build is also significantly reduced. It's actually going with the square, so it's exponential kind of order. So which means that, in other words, like, long story short, we could not increase the size of our cores anymore. So single core is kind of limited. Yes, we can like do 4 issue or 8 issue, but beyond that, it wasn't really helping. And this was usually what we call end of Dennard scaling or hitting the power wall. Okay? So after this, what happens is that, if you remember, I told you that we moved to the new regime, and that's called multi-core systems. So for this lecture and the next lecture, and maybe the one after that, we're going to talk about what happens beyond what we call a uniprocessor. So in uniprocessor, and this is what we have learned so far, we have multiple threads and multiple processes. We can share various different states between these threads. But generally, they use the same memory space and share the same physical cores and all that. There is like difference between a process and a thread. So for example, process has its own address space, while the thread is more of like a smaller portion. For those of you who have taken any operating system course, you'll probably spend a lot of time understanding the difference between thread and process. But generally, think about that. A program can also be broken down into smaller pieces, which you usually call threads. And we can have multi-thread applications. And generally, the system software, in other words, operating system, is the ones managing this different level of abstractions, the threads and scheduling of the threads, and so on and so forth. The important thing, though, is that in a uniprocessor, a single core processor, you can have multiple programs, you can have multiple processes, you can have multiple threads within the process. But at the end of the day, they are all sharing the same processor. Okay? And that's kind of what limits us. So in order to speed this up, we can increase the number of, like, for example, lanes that we have in the processor. But as I said, that's limited by the technology. Okay? And we talked about how we can make this process faster, as I said, with superscalar, and that's what we did. But as I said, unfortunately, there are kind of three big limitations in superscaling things. One is the power wall, as I said. The second is that there's going to be lots of data dependencies, so that we cannot really utilize the entire superscalar as much as we want. And the third is branch prediction at some point is going to be the main bottleneck, because if I have, let's say, 16 issues CPU, and then I have one misprediction, then I have to basically flush all the 16 instructions and move from somewhere else. So the penalty of misprediction is not going to be low. It's going to be significant. And you guys now are expert in branch prediction. You see that no matter how much time you spend, and you're not going to reach to the 100%. There's always lots of these various different behaviors that you cannot predict. Okay? And then, of course, we talked about out-of-order execution, and that helped a little bit with this, because now we can kind of like move things around and predict the future and run things speculatively and all that. And again, all of these contributed to that 52% per year improvement that we show in the first graph. But as I said, unfortunately, all of these techniques combined together will at some point reach to a limit, okay? And this usually shows itself in some form of underutilization. So if I just look at my functional units, okay? Let's say, for example, I have 4 different functional units, and I'm showing each functional units in each cycle. So the y-axis here is different cycles. And then let's say, if it's the solid, purplish, it means that it's not being used, and if it's white, it's being used. If we look at the functional units over time, and for example, if you look at your homework example, you will see that not all the functional units are active at all times, right? So yes, there are scenarios that you can make them active, or 3 out of 4 active, but in many, many cycles, there will be underutilization, which means that I have available resources, but for various different reasons, including data dependencies and all, I cannot really use that, right? So for example, this is terrible because essentially it means that I only use one functional unit out of 4, so at best I can get like IPC equal to 1 versus the IPC equal to 4 that I wanted to achieve, okay? Um, and yeah, so this is kind of like showing that. So what we can do in order to improve this? So how can we improve the utilization of my functional units first? And then we're going to talk about how we can go even beyond just one single core and move into the multi-core. So we're going to get there, okay? So the first thing that we do, and all the modern processors does, is interleaving programs, okay? So what I show you here and what we have discussed so far is there is one program and one program only, and you start kind of, feeding, fetching the instructions, decoding them, putting them into the reservation station, scheduling them, and so on and so forth. And as I said, since there is dependencies between instructions, then you're going to have this form of underutilizations, right? So that's fine. But what if I interleave 2 different programs? So let's say I have one program with this behavior, another program with this behavior. These are 2 separate programs, which means that they have no dependency whatsoever across each other. They have dependencies of their own, but X1 in this program has nothing to do with X1 in this other program. This is your browser, this is your, I don't know, Spotify. So these are kind of 2 different programs, nothing to do with each other, okay? So if I can somehow interleave these 2, so you see that they conveniently kind of complement each other, okay? This is what we usually call simultaneous multi-threading, or SMT. Intel used the word hyper-threading as well. So hyper-threading and multi-threading is the simultaneous multi-threading is the same name, but the more common name is SMT, and you have seen that SMT is actually quite common in almost every modern systems. So the idea of SMT is that let's utilize the pipeline for multiple programs at the same time. So it's not just a super scalar processor for single program that we have one PC and we kind of read things. And now we have 4 different PCs, for example, from 4 different applications. And a single instruction, for example, if you look at the reservation stations, you might see instructions for program A, instructions for program B, instructions for program C, and so on and so forth, depending on how many we can run at the same time, okay? This will make things incredibly more efficient in terms of utilization because now I have 4 times, for example, more opportunity for scheduling things, right? It's because now, even if one program has very dependent, like has high dependency, the others don't. Or for example, if I have misprediction in one program, all I need to do is flushing the instructions for that program. The others are not impacted at all, right? So there are all lots of these great things that I can do when I'm doing this simultaneous multi-threading. So how do we implement this? So this will requires lots of copying and redundancy, right? So now each thread needs its own PC, needs its own register file, needs its own logical logic for virtual address translation, needs its own page table, needs its own exception handling. We haven't talked about exception handling yet, but we're going to talk about it later. But for example, there are things that we don't need to share. We don't need to duplicate, right? For example, we can keep the same reservation station. Maybe we just need to have one extra column that's basically assigning the process ID or thread ID to each instruction, so that if I want to flush, then I just check that thread ID, right? Same story for ROB, same story for functional units, and so on and so forth. So I can just pass along the process ID as another identifier for each instructions, okay? So the data path kind of like would look like this, right? So you have kind of like parallel PCs
that they are all going to decode. And then from then on, we basically what we do is kind of like same instruction, but everything that we had before plus some form of a PID, for example, or 3ID.
That like now we pass everything with also like where this instruction belongs to. Uh, but everything else pretty much is the same, right? So you don't need to kind of like duplicate many things in your system. Uh, there is also another concept that I want you to also know and don't be confused with SMT, and that's what we call multitasking and context switching. So generally, even in single core machine without simultaneous multi-threading, you can run multiple applications, okay? And that's actually what happens in many, many systems. The difference is that in single core machines, when you have context switching, at any given point, you only run one application. So running applications becomes serialized, all right? And what happens is that your operating system typically takes care and handle this kind of switching between them. So for example, you will have one application running for some time. So you have one thread running for some time. Then you will have the process called context switch. Think about this as an interrupt or an exception. This is when you basically save the information that you do here, and information that you save is things like your PC, the status of your registers, the stack pointer, anything that is changing from one program to another, you will save it. Then you will load the other program's information. So you essentially replace your current register file with the other's program register file, your current stack pointer with the other's stack pointer, and so on. And then at this point, you just continue executing, but this time you execute thread 1 instead of thread 0. And you can keep back and forth switching between them, right? So in terms of the way that this processor will operate is that it has no idea which one is running. The operating system basically just takes over, copy things to and from various points of the data path, including register file and all, and then pass the control back to the processor to kind of continue executing, okay? But of course, this has this big overhead of context switching. So essentially, every time that we need to switch from one application to another application, we need to do the saving and reloading, which itself has lots of time, requires lots of time. But this gives us this kind of illusion that we have parallel processing, right? So if this is really fast, from an external point of view, from a user perspective, you never see that one program stops and the other program runs. You always see kind of a seamless execution of both. Yeah. This No, no. So the question is this in conjunction with multi? No, this is separate. So this is what we call context switching or single. This is only we have one core, and let's say we only have one. We can run one thread at a time. Okay. Multi-threading is like an advanced version of this. The idea is that why don't we interleave these together so that we don't need to wait for this and this. But the cost of that is that now what I've used to save, now I need duplicate of that. So I need two register files and so on. Yeah. Uh-huh. The question is when you're doing SMT, when you're running two different things, are you running two separate threads of the same process, or are you running two different processes? And the answer is that usually you can run any combination, basically. That's why you have this notion of threads, actually. So that you can schedule things at the thread granularity. So basically, you take a thread of one process and a thread of another process, and you run them together. Mm-hmm. Great. There is also different ways of doing SMT. Uh, so, and then the difference between them is level of granularity that you can have. So this is the picture that I've grabbed from this website. So number one, the top one is what a normal program would execute in a system. So if I have three programs, green, gray, and yellow, what will happen is that, let's say I have a 4-issue processor, so I can run 4 instructions at a time. In a normal system without any sort of SMT, what I would do is that I run green for some time, then I context switch and then run the next program. Gray would be basically the operating system program. This is the process required to do the context switching. And then at this point, I'm going to run the yellow program, which is like the second program, the second thread that we want to run. Okay? Then I can have what we call CMT. And CMT is what we call a coarse grain multithreading. Okay? The difference between coarse grain multithreading and regular conventional processor is that coarse grain multithreading handles the context switch inside the hardware itself. In other words, we don't pay the penalty of the operating system takes control and switching things. Think about that. I have the register file. I can just quickly copy within one cycle to run the next program. So that's what you will see, that the difference between this and this is that I no longer need to pay the context switch penalty. I can quickly switch from one program to another program. Okay? And then we can have what we call fine-grained multithreading, or FMT. The difference between CMT and FMT is that still for every single cycle, we only run one program. But the difference between this and this is that now that I can handle things in hardware, why don't I, at every cycle just select whatever I want? So I can basically, at every cycle, switch between program 1 to program 2 to program 3. And the ultimate solution is what we call the simultaneous multithreading, or SMT, which you not only switch per cycle, within each cycle, you also mesh them together. So this is how things will look like. So in every functional unit, for example, you might have 2 instructions for one program and 2 instructions for another program, and so on and so forth. And in terms of utilization, clearly it's clear that SMT gives you the best utilization, right? So you see very rare number of white squares in that bottom, figure, because at any given point you can find something and push it into the FU. But in terms of complexity, of course, SMT is significantly more complex than the others, because now you need to basically duplicate everything that you had for every single process to multiple processes. Okay? All right, so this is what we do, and as I said, all the modern processors do SMT. Big problem with SMT is security, actually, because now that I'm sharing lots of things, is that for the attackers, it's also very easy to extract a lot of things. So SMT is getting less and less popular these days for security reasons, especially in the cloud. Many of the systems no longer use SMT just for those reasons, because your program and another client's programs can be mapped into the same physical hardware, and that's terrible in terms of security. But as I said, in most modern systems, prior to being worried about security, SMT was the standard way of running things. Okay? So now the question is, can we go beyond SMT? And going beyond SMT means that now we need to scale the number of cores that we have, because the best we can do is just increasing the lanes in the core. But as I said, they had lots of these technological limitations. So that was the motivation of going beyond a single core machines, and that's, as I said, in early 2000, we introduced the idea of multi-core designs. In the rest of this lecture, I want to talk about different aspects of a multi-core design. Essentially, the first thing is how to leverage multiple programs. Why multi-core are going to give us more performance? That's number one. We're going to give you a little bit of the design choices, but then most of the lecture will be talks about the challenges that we face when we are moving from a single core machine to a multi-core machine. Specifically, we're going to have two big problems. One is called cache coherency problem, and the other one is called memory consistency problem. And we're going to focus on those two problems in this next few lectures when we're talking about these. Okay? So the idea of multi-core is this, right? So we're going to have nice kind of like, multiple applications, each one kind of like, focus on like assign nicely to each core. They kind of run in parallel and synchronize and nicely. The reality though is kind of like this, right? So it's not going to happen. There are lots of challenges that we need to fix. But it's kind of like the idea of parallelization in general, right? So that's what you want to achieve. Also to give you a little bit of background or history or kind of like a big picture, that not all the systems are necessarily multi-core. Lower end embedded systems are typically single core, and as I said, they are in-order processors. They don't have any support for operating system or virtual address. The PC level is usually 4 to 8 core systems. Excuse me. They are 4 to 8 wide. There are 4 to 8 wide superscalar processors. They are usually out of order. They have SMT. They have 3 level of cache. That's what you see in your laptops. And at server grade level, like Intel Xeon or AMD EPYC and all, we are talking about tens of cores. So we're talking about 64 cores, 128 cores. These are usually the numbers. So that's kind of like, the comparison. And then with more cores, of course, you need to scale out your caches and all as well, okay? So how does your multi-core system look like? Your multi-core system will look something like this, that you will have your cores, okay? And then you will have some form of an interconnect. Usually we call it a network on a chip or NOC or different ways of connecting them. And then you have your memory systems usually connected on the other side of the interconnect, okay? The first question that comes to mind is that where do we put our caches, right? Is our caches on this side or is there caches on this side? What should we do with our caches, okay? Before answering that questions, let's also think about how does multi-core help us. Multi-core helps you in two important aspects. The first aspect is helps you with multitasking. It basically takes the burden off of your SMT and allows you to run multiple programs at the same time. Especially if you're someone who's, your workload is lots and lots of these different tasks that you need to run at the same time, multi-core helps you with that. But multitasking doesn't necessarily give you performance. Multitasking is just more of a convenience, right? So like, now you can run multiple parallel, let's say, tabs in your browser and so on and so forth. What gives you performance and speed is what we call thread level parallelism, which means that if I can somehow break down a big program into multiple threads, multiple independent threads, and run them in the parallel, then that's where we're going to get performance improvement, okay? So keep that in mind. And as I said, the SMT already giving you some form of a multitasking, but it doesn't give you significant multi-level parallelism, okay? For multitasking, of course, there are various different questions that needs to be answered, including how do we schedule? If I have, let's say, 10 different tasks and I can only run 4 tasks, how do I decide which task to run? What are the power and performance overheads? And then when we are moving away to even larger systems, what will happen? These are the questions that you will see in an operating system course where we're talking about scheduling of different tasks and what should be the idea and so on and so forth. There's also another category of systems called real-time systems where there are some deadlines for a particular task. Think about like autonomous cars, right? So like you have to detect, I don't know, an object. Based on that, you need to take an action, right? And then at the same time, your Bluetooth also needs to be connected to the audio system of your car. Which one of these two tasks, both of these tasks are going to be assigned to the same computing system. But which one of these two tasks are more important? Which one should be scheduled first? And of course, the answer is first, right? This is a safety issue. Has to be real time. So if your Bluetooth connection is kind of scheduled later, nothing bad happens. So there's this kind of like considerations of how do we do the scheduling and all, which is again, it's more of a software problem really, and it's a separate course required for that to analyze this. But just keep in mind that these problems exist. Okay? What we want to talk about though is more of the second problem, the thread level parallelism, and how do we achieve this? And as I said, what are the challenges that comes out of this? Okay? So essentially the idea of TLP, and remember, I told you about DLP and ILP, and I told you at some point we're going to talk about TLP. So this is TLP, thread level parallelism. So the idea of TLP is that if I can somehow break down a program into multiple independent parts and run them all at the same time, then I'm going to have speed up, right? And if you remember, long time ago, we talked about Amdahl's law and told you that there is a limit to this as well, which means that there will be parts of your programs that are parallelizable, and there are parts of the programs that are sequential. And at the end of the day, you're going to be limited by those sequential parts. But there is still a lot of opportunity for the parallel part. So that's where this thread level parallelism comes into the play. To give you a simple example, let's say I want to put some 64,000 numbers together, right? So some form of a matrix, part of the matrix multiplication, okay? And I have 64 cores, okay? So here's the algorithm that I'm going to use. I'm going to basically assign a process ID for each core, okay? And I'm going to show it with 0 to 63. Then I'm going to partition this 64,000 numbers to 1,000 number partition and assign it to each core. Then I'm going to basically run this very simple algorithm, right? So the sum of P of n is equal to 0. Then I'm going to run a for loop that the index of the for loop is dependent on the process ID. So if Pn is equal to 0, it means that I get 0 to 1,000. If it's Pn is 1, I get 1,000 to 2,000, and so on and so forth. And each one will have their own partial sums, okay? So each one going to have its own partial sums. Then all I need to do is that one of the processors will be responsible to just gather all the partial sums together and get the final answer, right? And if you look at the complexity of this algorithm, you will see that the complexity of this algorithm is reduced by a factor of 64, just because that we are parallelizing the summation to 64, right? And there are tons of parallel algorithms that you probably have seen if you've taken algorithm course, like the famous one is divide and conquer, that you divide it into smaller pieces and you solve that smaller problem. This was an example of that. So all of those algorithms that you've learned about parallelism, this is where they're going to be used, okay? But not necessarily all of your algorithms can be parallelizable, right? So for example, if you need to read a file or something, if most of the activity you need to do is a sequential activity, then if you have million number of cores, that's not going to make your program faster. But if you have certain algorithms, you can make them faster by writing better algorithms for them, right? And the good news is that there are good portion of these applications that can benefit from parallelism. And actually, this kind of approach was the birth of GPU systems. That the idea was that, okay, now I have a good parallelism. Why don't I take this to even next level and have massive level of parallelism in what we call a general purpose, graphic processor units, GPUs. And the idea is there that I can even use more parallelism. And the beauty of that was that kind of idea, it was kind of a right place, right time kind of things that also matched with this boom in machine learning, which happens to have a lot of these summation problems that we have just described here. And these two married very nicely together, and now we have what we have. as explosion of using GPUs and hardware accelerators and all for machine learning, and kind of it's a win-win situation. So both are benefiting from this. So all of these ideas kind of like can be kind of simply explained by this fact that I can break down a program in machine learning is basically matrix multiplication, that kernel that I can break that down and run it on multiple cores at the same time. Okay? But of course, writing TLP and doing TLP is hard. It's not, as I said, given in many programs. For those of you have, how many of you have written a program in like MPI or pthread or CUDA? A few, okay. Yeah, so it's not like as easy as, let's say, writing in Python or C++ because you need to think about race conditions and different challenges that you're facing. There's also communication overheads because these programs need to be synchronized at some points, and there is also always sequential parts. So there are challenges with TLP as well, but it's also a very exciting area of research both at the software level, at the algorithm level, and so on and so forth. So like the bottom line is that n number of cores does not necessarily make your system n times faster, but ideally will give you n times faster. That's kind of the main motivation of a multi-core system. Okay? Reality, as I said, though, is kind of look like this. So you're expecting that everybody is kind of paralyzed, but the reality is that usually there's more like one core that's kind of reading and everybody else is idling. So you don't definitely want this to happen. And then how do we kind of improve this? Better algorithms, faster communications, and so on. So these are all goes under the umbrella of parallel programming, software, and algorithms. And again, separate course if you're interested about these things. All right. So what do we want to focus on is now we understand why we need it. We kind of understood how we can do it. So let's see how we can actually build it. Okay? So the main things that changes uh, from a single core machine to a multi-core thread level parallelism machine is the interactions with memory. Single instructions are the same. We have breakthrough in the project, I think. Single programs are the same. So like single instructions are the same. So your data path and controller for every single core does not change at all. What do change is the interaction with memory. Why do we have interaction with memory? Because you need to share data. If the multiple programs does not share anything, then you don't have parallelism at all, right? Remember that at the end of the day, these are part of the same program. They need to share. Since they need to share, the data needs to be shared. They need to access the same data at the same time, and that creates lots of challenges, as we're going to see. Okay? So that's kind of like what is fundamentally different between a multi-core and single-core system. Okay? So the questions that becomes now we need to answer is that how do we share memory and what should we do with our generally memory hierarchy, including our caches? Okay? So there are two options for your cache hierarchy or generally memory hierarchy. Remember I told you that I had core interconnect and memory systems? One option is I put my cache system here. Okay? This is what we call a shared cache system, which means that all the core access to the same cache, same way that I have access to the memory. Okay? The other option is what we call a private cache system, where every core has its own cache. Then they go to the interconnect, and then they go to the memory system. Okay? So this is what we call private, and the other one is called shared. So tell me, which one do you think is the better options, or what are the trade-offs? Like, what do you gain in each, and what do you lose in each? Yeah. Uh-huh. Mm-hmm. So it's slower because the cache is farther away, but it seems to be faster of management because of all this here. Okay? Any other suggestion? Yeah. Okay. So private cache is a little bit more expensive in hardware. All right. Any other suggestion? Yeah. So we're gonna have furnace issues, right? So some cores might like use more space and some might use less space, and that could negatively impact our system. You have something to say? Uh-huh. hmm Same, yeah. So we might have more conflict, so they tend to kick each other's out without really wanting to, right? So again, that's kind of leads to the furnace issue. Yeah. We might lead to correctness issue. Correctness issue is a no-no, so we want to fix that. But we're gonna actually lead into correctness issue. That's right. But we will fix it. hmm All right, yeah. So what you said are all correct. Um, again, we can just think about it in terms of the three things that we know already. Remember that all we care about is average access time, so hit time, miss rate, and miss penalty. So let's actually go this practice together. So in terms of hit time, uh, private versus shared. So this is private, this is shared. Which one has better hit time? Yeah. Private has better hit time. Why? Because it's like literally connected directly to the core versus shared needs to go through the interconnect and then to the cache, and interconnect is very slow. Okay? This is just physical limitations. Think about distance. Okay? But what about miss rate? So let's consider two scenarios. Let's say all the applications are quote unquote cache friendly, which means that they have spatial and temporal locality. In that case, which one of these two scenarios are better? Shared or private? Yeah, private. Why? But they're all cache friendly. So actually shared is better than private. The reason is you have better utilization. The same reason that you had better miss rate in fully associative versus direct map, same story applies here. So you're utilizing your space better. If, for example, one application needs 1/4 of the cache and the other one needs 1/2 of the cache, you can allow it to happen, right? So they can nicely fit together because you're sharing the entire space. Whoever wants how much, they can take it. But if I, yes. Yes, so that's actually the second case. If I have what we call a streaming application, which means that the applications keep requesting and not really using the cache that much, then we're going to have issue where the other one that was cache friendly now is also impacted by the poor performance of the other because of the conflict and all that, right? So in that case, your private cache is actually usually better than your shared cache if you have at least, because every cache, every program has its own isolated environment, so they can use that. The other one, the streaming one, is not going to use the cache anyway, so it doesn't matter whether you share it or you make it private. The other one that do use cache can now actually use it. So that's kind of the idea. You had a question? So when I say cache friendly, I mean that you benefit from having a cache, which means that it's not just compulsory misses, compulsory misses. I'm going to have some form of either temporal or spatial locality. Yeah. Yeah. So it's their stream, right? So it's going to be like 1, 2, 3, 4. Like think about watching a video, right? Like if you're watching a video, you're streaming your video. You never go back and watch like a frame again, and each frame is a piece of data. What about miss penalty? Miss penalty, yeah. Mm-hmm. Yeah, sort of. So you can argue that miss penalty in shared is better because you already paid the penalty for hit time. It also depends. If you have multiple caches here and multiple caches here, then for some of them doesn't matter because it still goes through the same process. But yeah, generally shared is better than private. Lastly, what if I want to share a data between them? Which one is a better option? So if I want to have thread level parallelism, let's say that partial sums, which of these two options are a better option? Shared, right? So because shared, I can just basically have this copy here, and I only need one copy, versus in private, I kind of need two copies or need to somehow figure out how to maintain copies. So sharing in a shared cache is much easier to do, okay? So keep that in mind. Uh, what we can do to kind of mitigate the advantages of disadvantages is that we typically go with a hybrid approach. Remember that I told you that we usually have multiple level of cache, right? So what we can do is that we typically have private caches in upper levels. So for example, we usually have L1 private cache, because L1, what is important in L1 is hit time, right? So if I want to maximize my hit time, I put L1 as private. But then the rest of the cache, I can put it as shared. So usually my last level cache, LLC, is usually shared. So typically what you see is that L1 and L2 are private caches, and L3 is shared among all the systems. So this is what we call a hybrid approach, okay? So you're going to have all the disadvantages and advantages that we said. So everything we said kind of applies to a hybrid method. Any questions here? Great. All right, so it seems to be that we have fixed the problem of multi-core. We just have a hybrid cache, and all we need to do is build it, and that's it, right? So that seems to be all we need to do. Of course, there is questions such as what sort of replacement policy should we use for a shared cache, and what should we do to make sure that the fairness is guaranteed and all. And these are the things that people have done. If you take an advanced computer architecture course, that's where we're going to talk about those things as well. But there are actually two big problems in this system, okay? The first problem is that shared caches, when we have both the shared data and private data, could unfortunately lead to correctness issues, okay? And that is usually what we call a coherency, because the content that we have in private caches are not going to be coherent. I'm going to give you a concrete example just in a minute. The second issue that we're going to have is, as I said, performance issues. Because, for example, if one cache tries to hide the entire LLC, then the other ones will be impacted by it. So there needs to be some check and balances for that. And as I said, this is more of on the replacement policy and all that we're not going to describe. But let's talk about this correctness issues. So specifically, there are two issues that we see in multi-core. And today, the rest of the lecture, we're going to talk about the first one. If I finish it, the next time, we're going to talk about the second one. So the first one is called what we call cache coherency issue. The issue with cache coherency is that at some point we may end up with incorrect copies in private caches, okay? If we didn't have private caches, we're not going to have a cache coherency problem. But as I said, we do want to have private caches, so we're going to have cache coherency problems, okay? The second problem, so actually let me talk about this first problem. The second problem is what we call consistency problems, and I'm going to get to that. But let's actually give you a little bit more example on why we have this issue. So let's say that I have two cores, core number 1 and core number 2. Let's say there is a memory MZ, Z is the address, and let's say initially Z is equal to 0, and say that Z is like, I don't know, an address, like 200, okay? And let's say, for example, X5 is equal to 10, okay? Just some arbitrary numbers, okay? So let's see what happens when I'm running this piece of code here. As I run core number 1, this is a load X0 and Z and load it to X1. So what I'm going to get is that this will be a cache miss. We're going to go to the memory and grab this value and put it here. So I'm going to store Z, 0 here, right? So Z equal to 0 here, all right? Then I'm going to do the same thing with core number 2, and then I'm going to read the same 0 here. Okay, so far so good. That's expected. Now let's say core number 1 decides to update the value of Z and wants to write X5. And as I said, X5 is 10. What will happen is that core 1 from the CPU side issues this 10. What it's going to do is that it's first going to check L1 and see that I already have Z. So what I'm going to do is that I'm going to update this value and put 10 here, okay? So now here's what's going to happen potentially. If this 10 stays here without updating and kind of like calling everybody else and telling them about that, oh, I updated something, what will happen is that if in future core 2 has another load to Z, since it's already cached the value, it's going to read this as 0, okay? So the assumption here is that I wrote to core number 1 wrote to that address. Since it's already in private cache, it's going to just update that private cache without telling anybody anything else. And others, no idea about there has been an update, going to read the value, see that, oh, great, it's actually in my cache already. I'm going to read it, but they're going to read a wrong value. And remember, these are all part of the same programs. We have what we call thread level parallelism. So the idea is that everybody should see the same value all the time. This is what we call a coherent value. So everybody, if one core writes 10, everybody else has to see 10. If they see other numbers, that will lead into correctness issues. Your system will break down. So your parallel algorithm not going to work, okay? So this is what we call a cache coherency problem, and obviously we need to fix it. The way to fix it, as we're going to talk about, is somehow updating everybody about every update. Sounds trivial, but there are tons of issues that we need to fix in order to achieve this cache coherency problem. The second problem is what we call memory consistency problem. The problem with memory consistency is the order. It's not the same address. It's the order of the writes that might lead into a problem, okay? So we are expecting that the order that we write things to the memory will be the same order that everybody sees. So if there are two consecutive stores to the same address, for example, or to the other address, the other programs should also see, the other processor should also see that the same order. But since we have out-of-order execution and we kind of move things around, the orders that I see may not be the order that the other processor sees. And that will lead into an issue. So let's talk about this. So let's say I have two programs. These are running at the same time. These are parallel programs. So what I'm going to have is something like this, okay? So in core number 1, I'm going to load Z to X1, okay? And let's say
z and y is initially equal to 0, okay? So I'm going to load z to x1. Then later on, I'm going to store x7 to y, okay? And these are two separate addresses. Z and y are not the same address. One is, I don't know, 100, the other one 200, okay? In the same core, that's not an issue. Even if I change the order, that's not an issue. On the other core, I'm going to have load y to x2, and then at some point later, I'm going to have store x8 to z. Now the question is, if I run this program, what are the possible values for x1 and x2? And can you tell me all the possible answers for this? And what should be the correct answer is another question. So can someone give me one possible answer for x1 and x2 in the system? And remember, these are out of order. Yeah. Uh, so let's say initially z is 0, 0. So x1 is 0, and then what is x2? Oh, 0. So we can have 0, 0. So, and then what is the sequence that leads to this? Can you give me the sequence? So I run, for example, this instruction first, then this instruction, then this instruction, and then this instruction. That will lead to this number, right? Can someone give me another potential output? Yeah. Mm-hmm. Yeah, so if I have 1, 2, 3, and 4, what I'm going to get? So x1 would be 0, but x2 will be this, right? So x7, which is 200, right? Another value. Yeah. What? 100 and 0. So the opposite of what we said. So if you have 1 and 2, and then 3 and 4, then we can have 100 and 0. Can we have 100 and 200? Anyone brave enough to say that we can have 100, 200? Yeah. Yeah. And we can do that because remember that we can have out of order execution. These are not necessarily related to each other, so I can actually reorder them in my own processor. And if the other processor don't see, or for any reason see the opposite ordering of this, what they will see is 200, 100. Okay? And that will lead into uh, a scenario. So to summarize, what happens with this program is that I'm going to, depending on which order this instruction runs, I'm going to have 4 different values for my x1 and x2. And that means that this is very, very challenging to get it right. And it means that, and then another big problem with the system is that if I run this multiple times, each time I might get a different results because the way that these instructions are going to reorder, we don't know because this is what we call a race condition. X1 might, process 1 might be faster than process 2. So this might run faster than this one. Or it could be other way around. Sometimes it could be interleaved. So there are multiple different solutions, okay? So how do we fix this synchronization problem? And this synchronization problem is basically we want to answer what is the order that we should see, and how can we
enforce that ordering. This is what we call the synchronization problem. It's collection of some software tricks that we're going to use. So we're going to use various different software primitives, such as barriers and locks and these kind of things, mutexes, that kind of like ensure the timing of this. But also we need in the hardware knows that what is possible and what is not possible. Can I reorder loads and stores? Does stores happens in order? Does loads happens in order? Does nothing happens in order? What is the order that we're going to see on the memory side? And that is very, very important because if those order changes, again, this value changes. So for example, if I have a load to store queue that doesn't allow loads and stores to be reordered, then you're not going to see 100, 200, right? Because if I only retire, since I know that I'm going to retire this first and retire this next, I always guarantee that this first, excuse me, the first one will happen first, and then the second one will happen, right? So there are these things that I need to know, and we're going to talk about all these kind of problems in more details and the solutions for it, okay? Performance we're not going to talk about, but let's talk about coherency and consistency. We're going to talk about coherency first for the rest of this lecture. If we finish it next time, we're going to talk about consistency, okay? So this is the problem that we have. Let's have a quick break. We're going to come back to it and see how we can fix this issue, all right? Let's continue. So remind you that we had this problem of coherency problem. It's when we are writing to the same address from different cores. And if I have a private cache, then I might have inconsistent copies. Remember that if we didn't have private cache and everything was shared, basically everybody was just seeing the same copy all the time, and that was great. But we need to have private caches. All right, so again, two questions that comes to mind is why do we share data? And I told you already, because of thread level parallelism, we do need to share data. The other question that you might ask is that why do we have private caches? And we need to have private caches for hit time reasons. So we cannot eliminate this problem. Okay, so the bottom line is that I need to deal and fix the issue of cache coherency. The easier solutions would have been not sharing or not having private cache, but neither of those two options are valid options in terms of performance. Okay? So what is a cache coherent system? A memory system, we call it coherent if you have these three things. Okay? If you have what we call read what is written, which means that a read of x on P1, I'm basically reading it from the slides because this is kind of like more of a formal explanation. So a read of x on P1 returns the value written by the most recent write to x on P1 if no other processor has written to x in between, right? So that's straightforward. This is like for single cores, we need to read what has been written. That's fairly straightforward. Then we need to have coherent writes happen eventually, which means that if P1 writes to X and P2 read X after a sufficient time, and if there are no other writes to X in between, P2 should read what's been written by P1, right? So what says here is that there will be some delays. We cannot do anything about that delay. But if we wait long enough, and that is the latency of our coherency protocol, P2 should be able to see what has been written by P1. That's what we need. That's basically the example that I gave you. Yeah. One, so the question is, what's the difference between 1 and 2? One is from the single core perspective. So it says that if I write to a value when I read it again, I should see what I've wrote. It basically says that you're not allowed to do read after write out of order execution, okay? Which seems very trivial because we have already talked about this and we have taken care of this. But we basically says that if you want to design a processor that decides to move things around, you're not allowed to move store before load. The third one is causality of writes, which means that if I write to the same location by two processes, they have to be serialized, right? Uh, Basically, writes to the same location should be seen similarly across all the different processes. Because at the end of the day, what matters is that the final value, which is the second write or third write, whatever, the last write, right? So the writes should be serialized, should be seen by same order across all the different processes. If I have these three conditions, then I'm going to have what we call a coherent cache. And every cache, every multi-core system do need to have a coherent cache. Otherwise, it will lead to incorrect numbers and breaks your systems. Okay? So the first question is, okay, can I fix this issue in software? Can I write a code that doesn't have a cache coherent problem in the first place? And the answer to that is no. The reason for this is cache is invisible to software. Basically, you have no control over what is cache and where is cache and which core is running that part of the program and all that. So you cannot write programs assuming that knowing where things is being stored. One possible option is not using caches at all. That will fix the problem, but that will mean that you have terrible performance. So nobody writes a program like that. So that's not a solution. The second question is, can I have maybe an instruction that does something with cache coherency? So, okay, I understand that I don't know in software, but can I have, let's say, flush things from the cache in the ISA? The answer to that is actually yes. So there are instructions, especially in x86, that can flush things out of the cache. And that will fix the issue of coherency. Because anytime that you want to read, all you need to do is flushing things out and reading it from the memory, right? Or after each write, make sure that you flush it out so that it updates the memory. So there are ways that you can do it. But it's not the greatest option in terms of efficiency, ease of programming, and performance. So you rarely see that people actually use this, but there are some highly optimized, very small codes that benefit from the ISA level flushing. Okay? So what is, and then the operating system, can the operating system fix this problem? The answer to that is also yes, but it also requires lots of involvement from the operating system. Because again, if after every single access, the operating system needs to take involved and flush things out and so on and so forth. So the answer to whether or not software can fix this is kind of a maybe, but it's not the most efficient way. As a result, we typically focus on hardware-based solutions to fix this issue. And this is what we call a cache coherency protocol. Okay? So essentially, what we need to do is that in hardware, we need to have a very well-defined process where after every single load and store, we need to know exactly what should we do. This is usually involve announcing that action to the other nearby cores. And those other nearby cores, they need to pick up that action and do something with it. So they need to update their values and so on. And everything also needs to be also communicated to the memory. So the memory also needs to be involved in this process. Okay? So essentially what we do is that we're going to use hardware to track this activity. So we're going to add a few more bits to our cache hierarchy to kind of keep track of what we call coherency states. We're going to kind of like augment our buses in order to kind of send and receive commands and messages between the cores. And then we're going to have some controllers for each of these caches in order to understand these activities and do some proper action. So that's kind of like the gist of what we're going to do in cache coherency protocols. Any questions? So what is the protocol we're going to use? We're going to use what we call snooping protocol. Okay? So we're going to snoop the cache and take proper actions based on that. And that would be the premise of our cache coherency structure. So how does the snooping works? So essentially think about this as I have my CPUs, I have my private caches, I'm going to have my what we call interconnect or memory bus, right? And I have my last level cache also connected to this memory bus. I have my main memory connected to this memory bus. I have my disk connected to this memory bus. What I'm going to add is this bus control that basically all it does is that it snoops. Every single transaction, it takes a note of that and do proper actions for it. Okay? So in order for the snooping to work, that everybody needs to cooperate, right? So for example, if there is any transaction between this CPU and its own private cache, not only this transaction should happen, but this cache should also broadcast this transaction to everybody else, okay? So for example, if that example that I gave you that I write to that address Z, not only I update my cache, but I also announce that Z has been updated to value X, right? So this is what is going to be broadcasted by this cache. Everybody else will snoop and listen, and they're going to take proper actions, okay? That's the idea of cache coherence. Okay, so let's talk about details. What do we need to store, and what are those things that we need to store? How many states do we need, and so on and so forth. So recall that we already have metadata in our cache. So for example, LRU states is an example of each cache line. So what we are suggesting is add more things to that kind of states. So this has nothing to do with the LRU states, but it's kind of using the same structure and infrastructure. Okay? So here's what we're going to do. Okay? So so you have to think about, okay, what are the possibilities, right? We're going to have a miss. We're going to have either a write miss or a read miss. Based on that, I need to do some simple things, okay? So this is what we call a Snoopy cache coherence, okay? So on the write miss, which means that I want to write, but it's not in the cache. So let's say I have 2 cores. I want to write to some address Z, and it's not in the private cache. So it's a miss. What should I do? Basically, the protocol tells us that whenever there is a write, everybody, including the same cache that we have, they have to invalidate their data. So if there is another cache here that they have the current copy of Z, if I see a write, I will invalidate my data. So I'll flush it out of my cache. It basically says that I have a copy, but this copy is no longer a valid copy because there will be a value that's going to written. So I'm going to just get rid of this value from my cache. I'm going to evict it from the cache, okay? And then the write can be performed. Basically, writes can go through the memory and update it. I can put the copy back to each cache. I may leave it there, and then next time I'm going to use it. This will lead into extra cache misses, because I used to have that, and then next time it would have been a hit, but now it's not. But this has to be done, otherwise I'm going to read an incorrect value. Okay? On the read miss, okay, so if I want to read some value and I don't have that value, what should I do? There are 2 possibilities, okay? The first possibility is that no one else has a copy of that data that I want, okay? In that case, I just go and grab it from the memory, okay? But a more complicated scenario is when there is another copy somewhere else in another memory, in another cache. And that copy is dirty. Remember that I told you that there are 2 ways of implementing a cache. There is write back and write through. The idea of write back was when I write, I don't announce it to the memory. I keep it to myself. Only when I evict it, I announce it to the memory. That's the dirty scenario. So the problem of reading is that if there is a dirty sample instance of that memory I want, that dirty sample needs to be written back to the memory. Then it's safe now for me to read it from the memory, right? Otherwise, if there is no dirty sample or nobody else has a copy of it, then it's safe to bring it from the memory. Okay? So these are the kind of like very basic way of reading things from a cache. Even more basic than this is, let me see. Uh, so basically, this is what we usually call MI, the Modify and Invalidate Coherence Protocol. Before that, basically, based on this thing, as you can see, I can basically fix this problem that I explained to you, right? So if I load Z here, if I load Z here, then when I write, I'll say that whenever I write, what happens is that I'm going to invalidate everything. So I'm going to invalidate this, I'm going to invalidate this, I'm going to write it to the main memory here. And this way, the next time that this is going to read this value, is going to read it from the memory, and we're going to fix this issue. So kind of a simple solution for this is that whenever I write, I just flush everything out of my cache, and then I move forward. Or if I don't want to flush everything, as I said before, this one gonna invalidate, this one gonna keep the data, but it's gonna keep it dirty. Next time that this one wants to read, it wants to read it, announce it that I want to read. Since this one has the dirty data, it's going to go and write it to the memory, and then this value will be read from the memory. So either of these two options. I'm going to give you more examples, so don't worry if you're not still fully following. But basically, what we need, the minimum that we need, is 2 different states. Okay. We need to have a valid copy, and it has to be the most updated. And if we don't have the valid copy, uh, 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 we need to go and grab it from the memory. Okay. Based on this, we're going to have what we call an MI coherence protocol. M stands for the modified state, and I stands for an invalid state. Okay. So basically, the way that this works is that let's say I have 3 different cores, okay? And I'm just talking about one address, but you can extend this to multiple addresses, okay? At the beginning, let's assume that none of these cores have the data in their cache, okay? If you don't have that particular value, you start with the invalid state, okay? Okay. So the way it works now is that, so you initially started in invalid state. Now let's say, for example, we have a various sequence. So let's say, for example, core number 1 wants to read, okay? If C1 wants to read, I'm showing it with like, actually, let me show it this way. So I show it R1, okay? I want to read a value. And 1 means that core 1 wants to read this value. I have 2 states. Either I don't have the value, and that is invalid, or I do have the value, and we call that modified, okay? So when R1 happens, core number 1 going to announce that I want to read this address. Let's call this address Z. So it's going to announce it to everyone else that I'm going to read this value. Since all of these guys already don't have this value, so they are in the I state, they don't need to do anything. They don't need to be worried about anything. They don't need to do anything. What happens is that I will transit to the M state, but core number 2 and core number 3 stays in the I state. Okay? So in this cycle, we will have core number 1 in the M state, core number 2 and core number 3 is in the I state. Okay.
Then, for example, let's say that core number 2 wants to write. Okay? So if one of the cores wants to write, what will happen is that all the cores needs to invalidate their data. So core number 1, which used to be M, now needs to go to I. Core number 3 is already in I, nothing to do. And core number 2 now needs to go to the modified state. Okay? So what happened is that we kind of like switching between these two cases. You got a question? Mm-hmm. Yeah, this is just the simplest format of coherence protocol with just two states. We're gonna later add 4 more to this, but this is like a bare bone way of doing cache coherence. Yeah, you had more question? Oh. 1 bit. Per line, you have 1 bit. That's it. Very simple. All right? So now let's, for example, say that core number 3 wants to read again. What will happen is that there are 2 options in this case. As I said, if I have the dirty bit, then remember that the copy that I have in the memory now, it's not updated. The updated copy is now in this core, right? So this core needs to write this data back to the memory, and then it has to be read from the memory to core number 3. So what will happen is that M needs to invalidate their data and write it back again to the memory. So this is invalidation plus writing back. Typically, in our homeworks and quizzes and all, we usually have something like a star to show that it's also written back. And then core number 3 now goes to the M state, and core number 1 stays in the I state. And this story continues. So whoever wants to read, the other one, since I have only 2 states, the other one has to go to the write back. So for example, let's say I have another R1. So here, although I don't have the stale copy, and I don't need to write back anything, since I only have M and I, and only one can stay in M, what I need to do is that this guy needs to go to M, this stays in I, and this one also goes to I. So we cannot have the same copy in both. Generally, by definition in MI, we cannot have the copy in 2 modified states because the name is modified. So we're assuming that only one of the caches has the data. But this is not the most accurate definition because in this case, neither of them are modified. But again, we need to invalidate. So it's an extra invalidate that needs to happen here, which is not necessary. But this is just a way that this protocol is because it's very simple. It's only 2 bit, 1 bit. That's how it works. Okay? Questions so far? Yeah. So the question is why here we are invalidating, because if I didn't, then I had 2 M's, and it's not allowed. Only 1 core can be in M. You cannot have 2 cores that both of them are modified, because then if I want to write back, I don't know which one, right? So that's why I only need 1. Later, I'm going to introduce a new state called shared state, S, and that's where these 2 are going to go to, and then we're going to fix this problem. Yeah. Yeah, these are caches of private caches of those cores. Mm-hmm. Yeah. So good question. The question is this block per cache? Is it entire cache? Is it set? Is it way? What is it? Typically, it's block, but you can also do set. So for example, if anything in that set is being accessed, you just invalidate the entire set. You can do that as well. If you want to reduce the overhead, but there is a trade-off. At best, you should do at block level, okay? Even better at the byte level. But we typically don't want to go that far. So we either stay in the block level or even go to the set level. The worst case would be entire thing per cache, which doesn't make any sense. Okay.
So we already talked about this problem that, okay, so R3 to R1 requires an unnecessary invalidation, which we don't want. So what we're going to do is that we're going to add what we call a shared state, okay? Because when we have reads, there is no need to invalidate. And invalidation, as you remember, will cause extra misses that I don't want. So I'm going to use an S and call this MSI, okay? So I'm going to have modified and invalid, now I add shared. So this is what we call an MSI cache coherence protocol, okay? At the end of this lecture, you will see 6 different words. So we're going to have 3 more of this added. So for now, we're going to have MSI, okay? So MSI, the way it works is this way. We're going to have the same addresses. Let's say all of them, again, starts in I, okay? Then let's say, for example, we will issue R1, okay? R1 will result core number 1 to to move. But since this is a read and it's not a write, we don't move to M state. We don't go to the modified state. We go to the S state, to the shared state, okay? So shared means that I have a shared but clean copy of data, okay? Now let's say, for example, we have W2. When I have W, so these guys stays in I. When I have W2 means that core number 2 wants to write. When I want to write, same rule apply here, that everybody has to invalidate themselves. So this one goes to I, this one goes to M, this one goes to I again, okay? Now what happens is that, let's say, for example, I have something like R3, okay? So R3, if you remember, I told you that the first thing that can happen is that uh, I need to write this back. So I need to invalidate myself and write this back. And then I go to the S state here. And this one goes to the I state here. That's one option of doing this. The other option of doing this is I write back, okay? But I don't go to I go to S. So I write back and go to S because now I can have my data shared, okay? So the second option is a little bit better because I maintain my copy of data. I just write it back to the memory such that the other value can also read it, okay? At this point, though, the value is clean, so we no longer need to keep the dirty bits. I do the write back and then go to the S state. If I just go to the S states, then we will have problems because the other core will read an incorrect value from the memory. So it has to be first write back, then going to the S state, okay? And then, for example, if R1 wants to read, then R1 can also go to the S state. So this one would be I. And then the third option would be at some point, all 3 can be in S state if all of them are having a clean copy of data, okay? And again, if at any point from now on, if anyone wants to read, they just read it from their own copy, and that's great. If anyone wants to write, everybody goes to invalidate, and that core goes to M, okay? And you can think about all these different variations, right? So the idea is that whoever wants to write, invalidate others. Whoever wants to read, others who has the dirty copy needs to write back, and then go to the S, and then this value can go to the S. If it's already in the S, they don't need to do anything, okay? That's the MSI protocol. This is kind of a state machine of that. So keep in mind that this could be, this is kind of like the transition. The one that you pay attention to is that if I'm in the M and someone else wants to write, I first write back and then go to S, okay? But then if I'm in M and someone else wants to write, I go to I. So if someone wants to write, I go to I. And typically, I write back as well because there might be some other memories that wants to see this. So Even if I'm in M, and then there is another core that wants to go to M, I need to go to I, but I always write back and then go to I. Just keep that in mind, because I want to see the same order of memory all the time. So the memory writes cannot be skipped. Always has to be fully completed. Okay? Any questions from MSI? Great. So after this, there is 3 more states. There is what we call E, there is one called F, then there is one called O. These 3 further optimize my cache. I'm going to explain each one by one and explain why we need them. But just keep in mind that many systems, you only use MSI, because MSI is basically the minimum that you want. The minimum that you want is MI, but MI is like too simple because there's so many unnecessary invalidation when you want to read a clean copy that almost no one use MI. What they use at the minimum is MSI. But with MSI, you are more than covered, so you don't need more than that. But many more advanced systems use what we call MESI or MOESI or MOESIF. This is kind of the ultimate version. So let's talk about those 3 optimizations. I'm going to quickly talk about one, and then in the next lecture, next week, I'm going to talk about the other 2. Okay? So what is the problem with MSI? Why we need to optimize it? So consider the scenario that a core is in S and it issues a write, okay? It needs to broadcast that, right? So if I want to write, I need to broadcast that so everybody goes to I, right? But now consider the scenario that I am the only one who is in the S. Why do I need to broadcast that to everyone else? Because if everybody else is already in I, broadcasting that does not gonna help in any way or in any way or form. It just creates an unnecessary extra broadcast, unnecessary work to everyone. Okay? So but what is the way that we know whether we are only one in S or whether it's shared among the others? That's where we're gonna introduce exclusive state. Exclusive means that if one cache or one block is in the E state, it means that no other cache is sharing that data. Okay? So we call that E state. The good thing about E state is that if I want to write, I don't announce it because I know for a fact that I'm the only one who has a copy of this data. I'm going to silently promote myself to M. Okay? And then from then on, if someone wants to read the data, I write back go to S. Okay? So the E state, it basically gives you what we call an MESI protocol, which basically what happens is that it's same as MSI. The only difference is that on a read miss, from I go to E first. So if I'm the first one if everyone is in I, the first read will result in I to E, not I to S. Okay? And if I'm in E and someone else wants to read it, I go from E to S. If I'm in E and someone wants to read it, I go from E to S because I no longer exclusive. I'm shared. Okay? But if I'm in E and I want to write, I go to M. Okay? But I don't announce anything. So the difference between MSI and MESI is that in MSI, if I'm in S and I'm only one in S, if I want to write, I still need to broadcast. In MESI, if I'm in E and when I want to go to M, I don't broadcast. So it saves a lot of bandwidth. And you may wonder why this is a big deal, because remember, many of the cache lines are not even shared between the cores. Most of these cache lines are actually exclusive to one core. So there are lots of these E to M, M to E actions for programs. And we don't want that to basically propagate to the rest of the network. Right? So if all you do is that you're just dealing with your own memory and your own addresses, then you technically you are always in E or M yourself. You don't need to broadcast anything to anyone else. right? Because remember, these things only changes if they're all written to the same address. If they're different addresses, nobody cares, okay? So this is the story of MESI. I'm going to next time give you an example of MESI. Then we're going to introduce F and O to further add more capabilities to the system. Don't forget your quiz on Thursday, and good luck with that. I'm not going to be here. I need to travel, but the TAs will be here. I'm going to probably join over Zoom or something to answer any questions if possible, but you're not going to see me there. I'm going to be in my office today from now until 3:30-ish. So if you have questions, comment, stop by and ask.